All right, so we're working our way towards the end of chapter 3 now. We've already covered measures of central tendency and measures of dispersion, and so we've saved the most complicated case for last. These are the measures of association, where what we're trying to do now is understand if there's a relationship between two different samples or two different populations, and if so, how strong is that relationship? So there's only the two basic measures of association that we need to cover. They're known as the covariance and the correlation. Now, before we start this, I just want to show you a graph, a special type of graph that is often used to help us understand if two variables are related to each other or not. So let's just say that we have the following situation. Imagine we're looking at sports, let's say, and so X will be the number of runs that a team scores every year, and Y could be the number of games that they win. Oops, games won, let's put it that way. So what we're going to do here is go back in time for a team and gather up information about how many runs they scored every year and how many games they won. So here's what we can do with this graph. Imagine that we plot a single point for single year's results. This could be, for example, year 2000. And let's say that in this year, this particular team scored 900 runs, and as a result, they won 89 games. And then let's say in another year, they scored 850 runs, but their pitching was really good that year, so they won 93 games. And then let's say there's another year where they really went nuts and they scored 1,000 runs. And so because of that, they're able to win 99 games. And so we can populate this graph. 1 point represents each year for however many years we're looking at. And so we're going to eventually find that there's a pattern of some kind emerging here. And so what I'd like you to notice here is that if I were to draw a line through these points, it would have a positive trend. And so what that's telling me is that there is a tendency, a strong tendency for the team to win more games when it scores more runs. And you can tell just by looking at this graph that, yes, in years when we score a lot of runs, we tend to win a lot of games, although it doesn't always work out that way. Otherwise, the points would all be right on that line. And the reason why they're not all on that line is because other variables influence how many games a team wins, in particular the pitching. You can have all the runs if you want. If your pitching isn't good, you're not necessarily going to win a lot of games. There have been a lot of teams throughout baseball history that had a lot of runs scored, and yet they didn't even make the playoffs because their pitching was so terrible. So, but at the same time, though, in general, the more runs a team scores, the more they tend to win. I mean, that is definitely one way to help yourself win more games by scoring more runs. Also, another factor that we don't see on these axes is the defense. I mean, obviously, the stronger your defense is, the more games you're going to win, regardless of how many runs you score. But just looking at these two variables only, what we're isolating is the relationship between runs scored and games won. And we're seeing a strong positive relationship between the two. So this type of graph is commonly used to analyze the relationship between two variables, and it's known as a scatter plot. So the scatter plot is a visual tool that lets us see if there's a strong relationship, or if not. I mean, it's possible that we have two variables that are not even related to each other. We could imagine, for example, let's say that we're analyzing the relationship between runs and revenues for the team. it's very possible that there is no relationship there at all. Although I guess in practice, teams that score a lot of runs are more exciting and maybe that would bring in more money. But if that was the case, if there's really no connection there, then the points would be sort of randomly scattered about. And the any line you drew through here would be flat. And so what's happening here is that there's no relationship between the two. And then finally, we could have something like this. Let's say that Y is now back to being games one, but X this time is runs allowed. In other words, by the pitching staff. So this is very different than the first case because more runs allowed is the surest way to lose games. Okay, so in other words, the worse your staff ERA is, the more games you're going to lose. So here we have a negative relationship between the two. And in the first case, there was clearly a positive relationship. So the graph is very helpful in that it can help us identify pretty quickly if there's a relationship of any kind, if it's positive, if it's negative. And also the scattering of the points can give us a sense of how strong this relationship is. Let's say that you've got two variables where there's a positive relationship. By the way, if you notice that in these graphs that I just drew, all the points are in the first quadrant because we can't have negative runs or negative games won. For some variables, though, we can have negatives and positives, so the points will tend to be scattered around the entire graph. But here, with this type of setup, we're looking at variables that must be 0 or positive. So all the information we have is in the first quadrant, but it doesn't have to work that way. So like in this next graph that I'm about to show you, we're going to have two variables that could be positive or negative. But what I really want you to see here is that even if both variables have a positive relationship, you notice the difference between the two cases is that on the left, the points are not particularly close to that line. So this, we could think of this as a weak but positive relationship. On the right, we could think of this as a strong positive relationship. And then the same thing is true with the negative relationships. So you can imagine that you've got over here, the relationship is negative, but again, the points are not particularly close to that line. Over here, they're very close. So on the left, we have what we would call a weak negative relationship. And over here, we have a strong negative relationship. So when we're analyzing a relationship between two variables, what we're really looking for is two things. Okay, so when analyzing a relationship between two variables, we are looking for one, the direction of the relationship, which means positive, negative, or no relationship. And number two, the strength of the relationship, meaning basically either strong or weak. Now, the graphs are fine as far as they go, but it's going to be challenging to compare two sets of variables with just graphs. We need a number. We'd like to have a number that we can point to that enables us to say this is the strength and the direction of that relationship. So that's what the covariance and correlation are designed to do. They're going to tell us, first of all, is there a relationship at all? And if there is it positive? Is it negative? And how strong is it? That's what these measures are designed to do. Now, unfortunately, they are a little bit messier than what we've been doing up to this point, but we'll get the hang of it with a little practice. So we'll start with the covariance. And then the covariance is set up so that if it is negative, that means we have a negative relationship, which means that the two variables tend to go in opposite directions. So in other words, just like the runs allowed in the games won. In other words, the more you give up, more runs you give up, the fewer games you'll win, and vice versa. So that graph would have a negative covariance attached to it. On the other hand, if the covariance is 0 or very close to it, you have two variables that are not really related to each other at all, like this one. Okay, and that's actually many variables are not related to each other at all. So this is not unusual. You to pick two variables that simply have nothing to do with each other, you would expect to find a covariance that's roughly equal to 0. And then the third possibility is, of course, that the covariance is positive, which means they both tend to rise or fall together, just like the runs scored and the games won. Okay, so with this graph, you would have a covariance that's positive. Now, the question is, how do we calculate this covariance measure? All right, now, just like when we had variances and standard deviations, there's two separate formulas, one for samples and one for populations, and the calculations are ever so slightly different for the two cases. The notation will be very similar to what we've seen up to this point. We'll be using the summation operator. But, all right, well, let's take a look at it. Oh, one more thing. This is something that's new. Since we have two samples, typically, although they could be populations, we need to make sure we know which is which. So one sample will be referred to as the X's and the other will be the Y's. Okay. So in other words, when you look at this formula, you'll notice there's Y's in here. So you've got, let's say, sample X. Could be something like this. And then sample Y would be, let's say, oops, what did I do? Obviously, this is Y2. And then we could define a mean for each of these. Here, for example, we have 0 plus 1 plus -1 over 3. So X bar is 0. Over here, Y bar is the sum of the Y's over N, which means 2 plus 4 plus 0 over 3, which is 2. So when you look at this formula, all of a sudden you realize there's not that much new going on here, except that all of a sudden we've introduced Y's. So you've got an element from sample X. And this is an element from sample Y. And of course, these two are the means of the two samples. And by the way, I forgot to mention this, but when we calculate this measure, both samples or populations, as the case may be, must have the same number of elements. Okay, that is a requirement for this measure. Both, we'll call them data sets, must have the same number of elements. And that number is N. Okay, so the N that we've seen earlier that represents the sample size, means in this case the common sample size between X and Y. Now, here's the only new thing we have to think about. You recall that earlier we saw S, plain old S, was used to represent the sample standard deviation. So we have to introduce some new notation now. So S is the sample standard deviation. If you're only dealing with a single sample, it should be self-explanatory which one you're referring to. But now all of a sudden there's two. So here's what we're going to do. SXY is the sample covariance. You can tell it's a covariance, not a standard deviation, because it has two subscripts. And then again, because we have two samples, we're going to write SX is the sample, or let's call it the standard deviation of sample X. And if you notice, you can tell because it only has a single subscript, and then therefore it must be clear that SY is the standard deviation of sample Y. All right, so for the rest of this chapter, I put those out there so you won't be confused when you see the notation. So now we're going to do a numerical example. We're going to work all the way through. We're going to take a set of data for samples X and Y, and we're going to calculate the covariance between them. All right, so first of all, here's the data. And so normally the very first thing you would do is calculate the means of the two samples. In other words, step one, compute X bar and Y bar. Now you can see just by looking at these, the sum here is 5. And over here, the sum is 15. So X bar, sum of the X's over N, is therefore 5 over 5, which is just 1. Over here, we'll do Y bar. Oops. Three. Okay, so we'll summarize that by saying, noting that X bar is 1 and Y bar is 3. Now, what do we do? Well, this is where it gets interesting. I'll tell you what, let me copy the formula back into the slide so we can see what it's all about. So this is where all the labor is going to go, basically. All the work is here. And you have to be really, really careful with this. What just happened? Oh, here it is. Here it is. My computer seems to be a little slow today. All right. So what this is actually telling us to do is you're going through each list. Actually, you know what? Let me do this too. Let me copy the data, or at least write it down. Yeah, I know there's not that much space in here, but I want it all to be together in one place if possible. Ooh. Yeah. Oh, okay. I might be able to get it to work. So by having everything together on one page, it'll be much easier to see what's going on. All right, so here's what I want you to notice. They're telling you to go through the entire list of X's and Y's one at a time, and in each case, subtract the respective X bar and Y bars. In other words, we'll start here. Here's X1, here's X bar. Here's Y1, and here's Y bar. And then we do it again. We go to the next row. X2 is -2. X bar is 1. Y2 is 2. And then we continue with the entire list. I don't know if I have enough room here. I'm so used to writing on the whiteboard. I have so much space, not here. All right, anyway, so this is of course then X3 minus X bar, Y3 minus Y bar. X4 minus X bar, Y4 minus Y bar. And then there's just one more at the end there. This will be X5 minus X bar, Y5 minus Y bar. Now, if you notice at the end, we're dividing not by n, but n minus 1. N is 5 because each sample has 5 observations. N minus 1 is 4. Anyway, so if you work out the numbers, do the calculations, you'll see that ultimately you end up with -4 divided by 4, which gives us a final result of -1. So you can see there's a lot of opportunities there to make mistakes. So we have to be extra careful with something like this. So, -1, what is that telling us? Well, we know that the relationship is negative. Now, we're going to get to this in a minute anyway, but I just want to mention that one of the drawbacks to this covariance measure is that the way it's defined, it's hard to be sure if that -1 refers to a strong negative relationship or a weak negative relationship. So we'll see what we can do about that in a few minutes. But first, I just want you to see what the population covariance formula looks like. We're not going to do a separate example with it right now, but I want you to see what it looks like and compare it with the sample covariance. And so you've noticed it's just, except for, now, remember with the variance and standard deviation, we had a different denominator. That's also going to be true here. Furthermore, oh, what happened? We've got something new. Now, this is the Greek letter sigma. Specifically, it's a lowercase sigma, which we've already seen. But we saw it used for a different purpose, didn't we? Yes, we did. We saw it being used for the population standard deviation. But if you notice, there's 2 subscripts here. Not only that, but look what happened here. We've got mu y and mu x. There's a subscript, which we never had before. So what exactly is the reasoning behind that? Well, once again, since we have 2 populations in this case, we have to have some way of telling them apart. So you can see right here on the next slide, it explains sigma xy is the covariance between the 2 populations. And by the way, don't forget, the rule of thumb is that the Greek letters represent populations or population measures. And then our alphabet, the Roman alphabet, are used to represent sample measures. That's how you can tell them apart. So this is the mean of population X and Y. And then I just want to throw in a quick reminder here, sigma by itself is the population standard deviation. There's no subscript because we're only looking at a single population. So it's the same process. It was the sample covariance except for that denominator. That is literally the only difference between the 2. So if you can do the sample covariance, you can certainly do this one. Now, the second measure of association is the correlation, or sometimes it's called the correlation coefficient. This one is closely related to the covariance. It's designed to offset the drawbacks to the covariance measure in the same way that the standard deviation is used to offset the difficulty with the variance that it is measured in squared units. Now, the covariance has two major problems that we'd like to address. Let me mention them here. Two issues with the covariance that make it less than perfect as a measure of association. It's not that there's something wrong with it. It's just it has issues that we'd like to correct. Number one, it has no upper or lower bounds. So it is difficult to interpret it. As I said before, we had a covariance of -1, and it's hard to say if that's a strong or weak negative relationship. Number two, it is affected by the units in which it is measured. Now, what exactly do I mean by that? Well, for example, suppose that a U.S. retailer has stores in the UK. The retailer would like to analyze or like to see if there's a correlation between sales in the US and sales in the UK, which is fine, but the resulting covariance will be different if the result of the data is measured in dollars or pounds. So in other words, the number that I will end up with will be different if I use dollars to measure all my sales or pounds. That's very awkward to deal with. It's not ideal. So the correlation coefficient, on the other hand, is determined. Now, it was designed this way on purpose, is bounded between -1 and +1, so it is easy to interpret. And number two, correlation coefficient is, we'll call it, I'll put in quotes, unit free. Okay, it is independent of the units in which the data is. In other words, in that study I was telling you about before with dollars and pounds, it doesn't make the slightest bit of difference if we use dollars or pounds. It will still be the same correlation either way. And you can see this is one reason why the correlation is really the preferred measure. So that's why you normally see it being done. Now, so again, you might ask yourself, well, why don't we just dispense with the covariance altogether? Well, here's why. The correlation coefficient is derived from the covariance measure. So we must calculate the covariance in order to calculate the correlation coefficient. So you can't not do the covariance, you have to have it. So think of it as the correlation as being an improvement over the covariance, just like the standard deviation is not just the square root of the variance. This one is related directly to the covariance, so we do need the one to calculate the other. Let me show you how that's done. First for a sample and then for a population. So the sample correlation measure, you can see, oh, now here's what's going on here. This is the sample covariance. This is the standard deviation for sample X. And that, of course, means this is the standard deviation for sample Y. And this is the new term. This is the correlation coefficient. And the subscripts tell me that this is between X and Y. Sometimes it's not always the case that we use the subscripts. Often in many books, they just write R because it's understood which two samples you're looking at. But over here with the S's, we have to have the subscripts because otherwise we might confuse them with something else. But the bottom line here is that, as I said before, in order to get to your correlation coefficient, you're taking your existing covariance that you just calculated, and then you divide by the product of the individual standard deviations for the two samples. Then you finally have your correlation coefficient. So it's a lot of work, but it's awfully, awfully important. You'll see a lot of applications for this in all of your business courses, especially in finance. In finance class, you'll see that you can use this to measure how well diversified a portfolio of stocks is. In other words, if you have stocks that are coming from different sectors of the economy, so that there isn't a whole lot of risk in there, you can measure how well diversified it is with a correlation measure. All right, so what we're going to do here is actually go through the steps of calculating the correlation for this last example, where all we did so far is calculate the covariance. So now what we need to do is calculate the standard deviations of these two samples. And of course, we've already done this, but it's good practice. Let me just copy this again. Just so you can see it all together in one place. Here we go. Also, with a quick reminder that X bar is 1 and Y bar is 3. So here, just the X, oh, here it is. It is a reminder right there. Okay. So remember how this works. Well, rather, I think I'll remind you of how this works. So you're going through, in each case, you take your X, you subtract the mean, then you square the term, add them up, and then divide by, and since this is a sample, you notice it's n minus 1. Now, by the way, what I've done here is I've gone directly to the standard deviation. The variance is what's under the square root sign. We don't really need that. We're going to directly calculate the standard deviation by taking the square root of this. And if you take out your calculator and plug in the numbers, you'll see that it's approximately equal to 2.1213. So just for your own practice, you might want to get out the old calculator, our friend the TI-84, which hopefully you have one by now. And go ahead and make sure that you can do this on your calculator. And when you're done, by the way, don't forget to take the square root. It's an easy mistake to make. Now for the Y's, of course, it's the same exact procedure. And so you run through all the Y's. And here's a reminder that Y bar is 3. And then, of course, you have to square these. Don't forget about that. By the way, if you forgot to square these, you'll know it right away because you'll always get 0. Okay. If you add up these differences without squaring them, you'll just get a 0. Okay, so then you take the sum of those, divide by 4, take the square root, and you'll wind up with about 2.2361. So finally, we're ready for the this measure. We combine all these to calculate our correlation coefficient, and you can see it's negative 0.2108. So it's negative, but it's not very negative. Remember, the correlation coefficient can go all the way up to -1, or I should say all the way down to -1. So think of this as a weak but negative relationship. Now, with a covariance of -1, it was hard to be sure. Here, it's easy. It's very obviously a weak negative relationship, something like this. Points are kind of scattered around. So you can see why this worked out so well. And also, there's no units attached to this, so it's the same no matter what units we're using. Okay, it doesn't matter if they're pounds or kilograms, whatever. All right, now the last thing we need to do in this chapter is show you the population version of this formula, and it is absolutely identical, except for the Greek letters. Okay, here's one you might not have run across before. This is the Greek letter rho. And whenever you see rho, almost without fail, it's used to refer to the correlation coefficient. You know, certain Greek letters tend to be used for the same thing all the time, and this is one of them. Like pi, for example, the number 3.141, et cetera, I've never in my life seen any book that referred to it as anything other than pi. I mean, that's pretty much a universal, and this is one too. So you can see the logic is the same. This is the population covariance. And this is the standard deviation of population X. And this is the standard deviation of population Y. And again, like I said before, unlike with the covariance, this will be the same whether we are dealing with a population or a sample. Okay, so that is one of the other things that's interesting about the correlation measure. I'll just throw this in here. Because of the way the correlation is defined, value of the sample correlation will equal the value of the population correlation. So I mean, you should make sure you know which is which, but you'll always get the same numerical results from both of them, which is not true with the covariance, which is not true with the variance, and which is not true with the standard deviation. All right, well, that's it for chapter 3. Now we're going to move on to something very different. Okay, so the next chapter will be a lot less computationally intensive, but it will be a little bit more, let's say, theoretical. You may be happy to hear. So let's get 5 going here. So what we're going to do here is introduce something called probability theory. Now, all of statistics is ultimately based on probability theory. Remember, the whole point of statistics is to explain what's happening in the real world in the presence of uncertainty. A lot of results are, of course, only going to be approximately true because there's a lot of things we simply don't know when we derive these measures. So probability theory is an attempt to create a mathematical framework to explain what's happening in an uncertain world. So we start out by considering the idea of what's called a random experiment. which is some kind of a process that generates results. Now, with this random experiment, we're going to assume that all the possible outcomes of this experiment are known to us in advance, but we do not know which one will actually occur. And you can use this to describe a lot of situations, but I find that games of chance are easiest to explain in the context of a random experiment. Like, for example, spinning a roulette wheel. Now, if you've never seen a roulette wheel, it's just a big wheel with numbers on it. Okay. Now, you may have seen this on TV. Every so often in James Bond movie, he might be playing roulette. But anyway, the way it works is that there are numbers from 1 to 36 and 0 and 00. And the slots are set up so that all these numbers are equally likely to turn up. Because spin the wheel, a little ball goes in, and it lands on one of the numbers. The 1 through 36 alternate between red and black, and these are both green. And so what's happening is that you place your bet on the table, and then they spin the wheel and see if you won or not. I mean, it's really that simple. But the key here is that when you spin the wheel, there's only 38 possible outcomes. 38 equally likely possible outcomes. Now, of course, you don't know what's coming up, but you do know at least that before you put your money down on the table, that there's 38 possible outcomes, all of which are equally likely. Now, choosing a card from a deck. I'm sure we all know that there's 52 cards in a deck. So when you pick a card, all 52 of them are equally likely to be chosen. So we know what could happen when we pick a card. We just don't know which card will come up. And of course, if we roll a pair of dice, there's actually 36 possible outcomes. Now, most games, we're not so much interested in the rolls. Like, for example, 1, 2 is one possible outcome. We're normally interested in the sums. Okay, and as far as that goes, the sums are everything from 2 to 12, but they're not all equally likely. Whereas these 36 possible outcomes are all equally likely. But all three of these qualify as random experiments because, again, this process is being repeated over and over again. And we know before we start what could potentially happen. We also know the probabilities of these events happening, but the only thing that's missing is we don't know what's going to happen. So what we would like to be able to do with probability theory is say, well, listen, I'm going to roll a pair of dice. What's the probability of getting a 7? Or what's the probability of getting an 11? Or I'm playing roulette. What's the probability of getting a red number? Those are the things I can do with probability theory. Now, probability theory has a very long and interesting history. A lot of it was created by a gentleman named Blaise Pascal, who you may have heard of. He lived in the 17th century. He was actually a theologian. He was a priest. And a friend of his was a member of the nobility in France. And he just said, Pascal, I need your help. I love to play games of dice, but I don't know how they work. I don't understand how the odds are set. So Pascal set out and wrote a treatise about probability to help his friend. And he did create a lot of important results in probability theory. But after a while, he got tired of it and went back to being a priest. But while he was busy writing these articles, he really contributed a lot to what is now known as modern probability theory. If you're interested, you can look them up on the internet. Wikipedia has an article about everybody, I think, who's got any claim to fame at all. Let me just show it to you real fast. Like I said, my computer is very slow today. So if it doesn't show up, well, just remember that name if you're interested in reading more about him. All right. Well, forget that. So anyway, We're going to use an experiment throughout this chapter, a very simple one. Now we're going to use dice, but we don't want to deal with 36 outcomes. So here's what we're doing. We're going to assume that we're playing some kind of game where the only thing that matters as far as winning goes is whether or not the dice are even or odd. Okay. So the game consists of rolling a die twice. Roll the die, you pick it up, you roll it again. We're going to record whether the rolls are even or odd. The reason we're doing this is because then there's only 4 possible outcomes, and that makes things a lot simpler for us. So here's the set of possible outcomes of this experiment. These are sets, by the way. And what you're seeing here is what happened in the first roll. And here's what happened on the second roll. Now, to make this notation even a little simpler, this one, we're going to write this as EE, EO, OE, and finally OO. So the set of all possible outcomes of this experiment is going to be EE, EO, OE, and OO. So that's the starting point for our experiment. We need to know what are we doing and what kind of outcomes are possible. So we did say that for this, we need to know what could happen. And so we gather up all those outcomes, as they're called, into a special set, whose name is the sample space. Okay. So all the possible outcomes are gathered up into a very special set, which we're going to call from now on the sample space. Sometimes in some books, they call it the universal set, but we're just going to stick with the name sample space. Now, here's an interesting side note. We know that the probability of getting an odd number on a single roll is 3 out of 6, or 1/2. And the probability of an even number is the same. So that being the case, what's the probability of getting something like this? EE means an even followed by another even. It's just a quarter. And you'll notice pretty quickly that at least for this particular case, and it doesn't always work out this way, by the way, all the possible outcomes of this experiment have the same probability. And now that is something that can actually come in very helpful. It will speed up our calculations, but we also have to keep in mind that it only works for these special cases. And then, of course, OO, same thing. 1/2 times 1/2, which is a quarter. All right. So that we need to know that up front, and then we'll use that information as we go along. Now, what we're trying to do is figure out the likelihood of certain things happening. So, for example, now we're going to define now a very important concept, and this is the notion of an event. And you notice it's defined as a subset of the sample space. Now, we reviewed set theory briefly the other day. A subset is a set that's contained within a larger set. So just as a quick example here, remembering that S equals the set that contains EE, EO, OE, and OO, I want to define an event, so I've chosen at most one even number turns up. So that means we're looking at the outcomes EO, OE, and OO. Because in each case, there's either one or no even numbers. You notice F is a set. Specifically, it is a subset of the sample space. And therefore, it qualifies as an event. So how do we calculate its probability? Well, that turns out to be a very simple matter because, among other reasons, they're all equally likely. So we could do this. So since F contains the outcomes EO, OE, and OO, it stands to reason that the probability of this happening is 3 out of 4. Now, here's a shortcut, though. When all outcomes are equally likely, the probability can be expressed as number of elements in this F over the number of elements in the sample space. No, you don't even have to add them up like that. You can just say, well, listen, there's 3 elements in F, there's 4 in the sample space, therefore the probability must be 3/4. But this is only true when they're all equally likely. What you're seeing here is always true. No matter what's going on with the sample space, with the experiment, you can calculate the probability of an event by adding up the individual outcomes in that set. But to further simplify things, if the outcomes are all equally likely anyway, then you can just count them. And here we would have 3 out of 4. I'll write that as number F over number S, which is 3/4. Okay, so either way, you're going to get the same thing. Okay. Now, what's coming up next is an example where the outcomes are not equally likely. And so we'll do another example, but I think we'll stop here. And the next time we meet, we will look at this example and we'll carry on. This is a very complex chapter, but we're setting up the foundations for everything that follows. So we won't need to use the calculators quite so much, but we will need to understand what we're doing with these concepts. So in other words, it's more conceptual than computational. So anyway, we'll stop it right here, and I'll see you all next time.